Hi, this is the solutions to sheet 3 of section 14 polynomials in my Formalising mathematics course. We're on the way to proving the Hilbert Basis Theorem. So on the way we define something called Orc's ideal IN. So what's going on here? So R is a commutative ring, I is an ideal of the polynomial ring R of X. So I is an ideal of the polynomial ring over R. And this Orc's ideal IN is an ideal of R, and it's the following ideal. It's 0, and then it's all the coefficients of x to the n in the polynomials of degree n which are in the ideal I. So it's not immediately obvious why that's an ideal, but you can rewrite it as saying you take I is an ideal of the polynomial ring, but you can think of it, so I is an Rx submodule of Rx, but you can think of it as a R submodule of Rx. That's what this restrict scalars is. And then you can intersect it with the polynomials of degree at most n, and that gives you a submodule, an R submodule of Rx. And then you look at the image of that R submodule under the coefficient map. And the image of an ideal is an ideal. The image of a submodule is a submodule as long as the map is an R linear map. And that's exactly why we use L coef, not coef. So there's the definition of the auxiliary ideal. And the first thing we've got to prove is that Orc's ideal IN is at most Orc's ideal, is contained in Orc's ideal IN plus 1. So this basically says if you're a polynomial of degree n in I, then your leading coefficient is also the leading coefficient of some polynomial of degree n plus 1. And of course the proof is, well, why don't we use x times the polynomial? Because if f is in I, then x times f will also be in I, because I is in Rx ideal. So that's going to be the proof. So let's intros P. Let's rintros. Let P be the polynomial, and then HP says it's in this Orc's ideal. But this Orc's ideal we can just take apart, right? It's the image. This map here is the push forward of a submodule, so the image of a submodule. So HP actually says that there exists an element upstairs which hits P is a lousy letter. Let me call it R. P is not a polynomial. So HR says that there exists a polynomial upstairs. So we can do P HP whose image is R. You see, there's some. There. This says that the coefficient of x to the n of P is R, and P also has all these nice properties. So it's in, I guess, so HP is an and, so we could do HP1, HP2, and there we go. So P is now in this submodule we're pushing forward, and the coefficient of P is equal to R, but R is only mentioned as this kind of arbitrary variable. R is an arbitrary element of capital R, so we can use the REFL trick here. We can put RUFL there, and now we don't have any R at all. And so we've got to prove that the leading coefficient, the coefficient of x to the n in P, because this says P has got degree at most n, right? Well, in fact, what does this say? This says P is in the intersection of two modules. So we can actually split that up. HP1, HP2 there. And now HP1 says P is in some restricted scale. That HP1 just says P is in I. We can even make it say P is in I, I suspect. Can we do this? P is in I. Rintro lets you give type ascriptions. Yeah, there we go. And HP2 says P is in these polynomials. I wonder what the up arrow is. The coercion from the submodule to the set. So P is in the underlying set of the polynomials of degree at most n. So this just says that the nat degree of P is at most n. I think definitionally, let's try this. P dot nat degree is less than or equal to n. There we go. So now our hypotheses are kind of clean. We've got a polynomial in I and its degree is at most n, and now we're interested in the coefficient of x to the n, and we claim it's in the ideal of coefficients of x to the n plus 1 in polynomials of degree n plus 1. So this is where we need to use P times x, I guess, because my guess is that this is change exists something something. Can I do that? Yeah, you see the goal is actually exists. There exists a polynomial. There exists a polynomial which is in I and has degree at most n plus 1, and the coefficient of x to the n plus 1 is the same as the coefficient of x to the n in P. So this polynomial is P times x. So we can use, or x times P. Let's use P times x, because we're going to have to prove it's got degree at most n plus 1. And so it would be handy if P had degree n and x had degree 1, you see. So we can use P times x, and now the goal is an and so in fact we could use refine for this. I mean, we could use P times x, and then we could split it there, and now we've got two goals. And in fact this goal also could be split, right? Because it says that P times x is in the intersection of two modules, so it says P times x is in the first one and in the second one. Yeah, now we've got three goals, but we could do all of that with refine, right? Refine P times x, and then we split the first goal, and then the second goal we left alone. So now we've got three goals, and so now we need sorry. And the first goal says what? It says P times x is in I, so we could actually change that to P times x is in I, right? And the reason that's true is because P is in I, and so we can use this I dot mul mem right, exact I dot mul mem right. I guess it would be x, is it? No. Oh, we need underscore. Yeah, we need to fill in the proof. You see, we've got an error there. We've got a, maybe I should just tell you what I was thinking now. I put exact, and then I kind of guessed I guessed a proof of this, but it's not quite right. You can see what it says. It says, no, the thing you've written is a proof that something implies this, and the thing that implies that looks really, really close to what we want, right? So clearly, we want another input. We want the proof that P is in I, and then it will spit out a proof that P times X is in I, which is what we want. So we're missing an input of HP1 there. So that's the proof of that. And of course, the change isn't necessary because exactness sees through definitional equality. And so because that's exactly that, we don't even need to have a case for that. We could just put that there. In fact, we probably don't even need the brackets. Yeah, so now that can go. And now what? This says P times X. What does this say? This says P times X. So this says change P times X dot nat degree is less than or equal to something. There we go. You see, it's really nice now, right? All the hypotheses and the goal, they're very clean. It's very clear, what they're saying. So now what? We know that the nat degree we know that P's got degree at most n, and we want P times X has got degree at most n plus 1. So it would be nice to know something about the degree of a product, right? So let's have H colon equals, I don't know, nat degree mul. Let's have a look at nat degree mul. Is that a thing? There's lots of nat degree muls. There's nat degree mul. Oh, you see, nat degree mul is of no good to us because it's got all these hypotheses that P is not 0. We don't really, I guess, we don't care if there's degeneracy. I don't care if, I don't care if the degree of X happens to be 0, not 1, because, because R is the 0 ring or whatever. I'm not going to be able to supply those proofs that things that polynomials are non-zero. And similarly, I'm not going to be able to supply a proof that a leading coefficient is non-zero. So this is what I want, right? It's nat degree mul LE. Because I only need inequalities. Nat degree mul LE says the nat degree of the product is at most the sum of the nat degrees. So we can apply that next, right? This is we can use the transitivity tactic, if you like. Transitivity. There. And now we've got to prove that the product is at most something rather, and now we could use exactly this, right? We could use exactly this, I would imagine. Yeah, we've pulled off transitivity. So in fact, this is refine LE trans this thing here, and then an underscore, right? Yes. So now how are we going to prove that? So we know that the degree of p is at most n, and we're going to know that somewhere there'll be the proof that the degree of x is at most 1. So we want to prove that a is less than or equal to b and c is less than or equal to d, then a plus c is less than or equal to b plus d, and that's going to be called like add LE add or something. Add LE add. There you see, now we've got 2 goals, and the first goal is the next input to add LE add, right? Add LE add. You see what it says? It says if a is less than or equal to b and c is less than or equal to d, then a plus c is less than or equal to b plus d. So the next input it needs is h. You can see the first goal is HP2, so we can just put HP2 there, and then this goal here. Hopefully this is library search, or if not, it's going to be called nat degree. Oh, it is. Yeah, nat degree XLE exactly. So that's the proof of that, and you can see you don't need the change. You know, the refine. You could change this to a refine, and then probably put an underscore at the end. You see, you could absolutely make this into quite a long. We don't need the change. It was just sort of useful to work out the proof, but that's just a very long term, right? You can just copy nat degree XLE into that underscore, and then copy its entirety of that into that underscore. But anyway, now how are we going to do this one? Well, this is in the library already. The n plus first coefficient of p times x is the nth coefficient of p, and let's call this thing here. So let's apply this, and there we go. That's done that one. So that says that the ideal at level n, you know, the nth auxiliary ideal is a subset of the n plus first auxiliary ideal. And so now we want to know this much stronger. Well, it looks sort of superficially much stronger. If a is less than or equal to b, then aux ideal a, aux ideal IA is less than or equal to aux ideal IB. But there'll be a lemma for that, right? Apply. I mean, the point is we should be able to deduce it from mono aux. So apply monotone of something. Monotone. This LE suck. This looks good, doesn't it? Because that's exactly what we've just proved. LE suck. So what happens if we apply that? It says it can't unify it. That's fine. Let's give it a. Oh, it's the apply bug. There we go. So we've applied that. I mean, perhaps we should stay away from the apply bug. Refine. Yeah, there we go. Refine that. And then this statement is exactly mono aux, right? Apply mono aux. There you go. Or we could just do exact monotone. I mean, I've claimed it's a one-liner, so let's do exact monotone mono aux. It wanted the I. No. Oh, hard luck. Oh, is it mono aux underscore or something? Bingo, got it. And so now this is begin exact end. So we could just prove it like that. And now what? So that's the end of this aux ideal monotone stuff. And so now finally we're going to do some lifting. So what's going on here? The idea is this aux ideal is defined to be the image. It's defined to be the image of a submodule of the polynomial ring. So we've got this L coef map, right? We've got this. We push forward a submodule of the polynomial ring, and we get a submodule of the ring, i.e., an ideal of the ring. And so that means that we should be able, given something in the ideal, in the auxiliary ideal, we should be able to lift it, right? We know it's come from something in the submodule, because this ideal was defined to be the image of some map, of some ring homomorphism. And so this is what we do here. We have this submodule mem map. This is the existence statement. This is the existence statement. There exists something upstairs. Such that its image is the thing downstairs. and it's just an abstract existence statement, but we use classical dot sum. We use classical dot sum to pull out the actual to pull out the actual polynomial. So we're starting with an element of the ring, and we're getting an element of the polynomial. And this isn't a ring homomorphism or a module homomorphism or anything. This is sort of a completely arbitrary splitting of this thing. So that's why it's just a lift rather than a ring homomorphism or a module homomorphism or a group homomorphism or anything. So there's lift, and now lift def says this. This lift of R is exactly. So I've chosen to lift every element of R. If R is in the ideal, then we lift it. Then we choose something that maps onto it. And if R is not in the ideal, then we just lift it to 0. So the definition of this should be, the proof of this should be REFL, because this is just true by definition. But we can use this to rewrite, you see. For example, this lemma here, we can rewrite lift deft. There, and so now we've got our goal is this decidable. So we have this hypothesis that R is not in the Orcs ideal, and then the goal is, well, if R is in the Orcs ideal, then we have to prove this. Well, if R is in the Orcs ideal, then it's this, and if R isn't in the Orcs ideal, then it's 0. We have to prove that that thing equals 0. So we need to know something about the API for Dite, and it's a diff neg, right? Rewrite diff neg. There, it's a diff neg is the hypothesis that diff neg changes a Dite to the conclusion of the negative one, under the assumption that the negative one is true. And we have the proof that the negative one is true. We have the proof HR there, so we can just do that. And in fact, it's probably exact. I would imagine it's exact diff neg HR, yeah. And because lift def is definitional, we don't need to use it, right? So then, again, we could get out of tactimo completely if we wanted. So now what? Lift mem. Why is the lift in the place where it's supposed to be? Well, that's going to be some spec. Yeah, we need this statement here. We need that statement there. So, so we don't have. So if I do this, then it won't work because we don't have HR yet. I see we don't have the hypothesis, right? So this we can't use yet because we don't know whether R is in. I think this one we need to do a case split. If R is not in the ideal, then this lift is 0, and 0 is in every ideal, in every submodule. And if R is in the ideal, then we use. Then this is a classical dot sum, and we need to use a classical dot sum spec. So we need to split on the cases, so we could rewrite lift def there. And now, yeah, this is a theorem. We can use things like splitifs because we're trying to prove a theorem. So splitifs is great. Splitifs is a very easy way of making progress with Dite goals, with if then goals, and this is a dependent if then. So if I do splitifs, thank you, Gabriel Ebner. Then we have two goals, and you see the first goal, we have this hypothesis. Can we name that? We've called it HR before. Splitifs with HR. Does that? Yeah, that looks good. Splitifs with HR. So now we've got two goals. And now the first goal, that's now when we can use this, because now we have an HR, right? There. And then the second goal, we'll just sorry for now. So what does this have say? What does this say? You see, we use the axiom of choice. We use classical dot sum, and this is precisely the information we threw away. It's a classical dot sum spec. So this says the goal is true, and also if you map lift down using elco, you get R. Okay, so we better remember that we're not going to use all of classical dot sum spec, right? We're just going to use half of it. So this is exact this dot 1. So there we go. So we've never used this dot 2. And in this situation, R isn't in the ideal. So we've just got to prove that 0 is in this module. And so that's going to be submodule dot 0 mem, right? 0 is in every submodule. Yeah, so that's done that. So there we go. So we only used half of the the axiom of choice thing. So maybe I'll make a comment there. We never used this there. Let's copy that. We never used this. There, we threw that information away. And I guess we'll need it later because it certainly, I mean, we'll certainly need it at some point. So now what? How do I know that this lift is in I? Well, I've just proved that this lift is in the intersection of I and MRN. And so that's going to be exact lift mem dot 1, I should think. Yes, excellent. And how do I know that the nat degree is at most n? Well, lift mem dot 2 will be the statement that that the degree is at most, that the polynomial is in the this submodule of polynomials of degree at most n. So that's by definition the nat degree is at most n. So this is going to be exact lift mem dot 2, I suspect. Yes. And now finally lift spec. You see, this is the information we threw away. So great. So we're in this hypothesis where we know that R is in the ideal because it's not true otherwise. You see, otherwise the lift is just 0. And so we've got the lift. I guess we want to rewrite lift def there, and then we can use. Now we've got this DIPE, this dependent if then else. But we know the if then else. You see, we've got this hypothesis that the if HR is the hypothesis, it's true. So it's rewrite diff pos HR. And now we've got to prove this thing here, and that's exactly the thing we threw away. So now it's just going to be this thing here, right? So it's just going to be exact this dot 2 there. So now we used it. Oh, and that appears to be the end of the sheet. So there you go. I shall stop talking. Thanks for watching.